Welcome everybody, this is Mr. the Visitor once again, and this time I want us to look at chemical formulas. This is not going to be a complete tutorial. We will just go through some of the most basic things which are very much necessary for us to understand. So we have 2.4 chemical formulas, the learning objectives. By the end of this section, you will be able to symbolize the composition of molecules using the molecular formula and the empirical formula. You will be able to represent the bonding arrangement of atoms within molecules using structural formulas. So very important. We symbolize the composition of molecules using molecular formulas. Just to find the composition, how many atoms are there, and we will shorten that molecular formula by using the empirical formula by dividing, for example, by a number that can go into the entire molecule without leaving a remainder. But we will see that. Secondly, we will represent the bonding arrangements of atoms within the molecules using the structural formulas. Sometimes we will use the ball and the stick model just to give us an overview of what is happening. Now, a molecular formula, what is it? It is a representation of a molecule because it is a molecular. So it is a representation of a molecule that uses chemical symbols to indicate the types of atoms, followed by the subscript to show the number of atoms of each type in the molecule. Very important. So this molecular formula represents a molecule because you have more than one atoms bonded together in a fixed ratio, and this molecule uses chemical symbols to indicate the types of atoms. Remember, these atoms of bond chemically. There is a chemical reaction that has to transpire in order to have this molecule. This reaction, this chemical reaction that is taking place has to accommodate certain number of atoms. They have to be balanced for the reaction to happen in the right way and the right procedure. And remember, not you telling how the molecules should bond, molecules themselves allowing themselves to bond with those which they require to bond with. So we are therefore saying that a molecular formula is a representation of molecule that uses chemical symbols to indicate the types of atoms. Chlorine maybe reacts with hydrogen and so on. So these are the types of atoms that we are speaking about, followed by the subscripts to show the number of atoms of each type in the molecule. So the ratio of the atoms that has to bond plays a very significant role. We symbolize them as a subscript. You will see that. Right. Now let us continue. A subscript is used only when more than one type of an atom given type is present. So when you have only one atom, for example, that bonds with other atoms, maybe one atom bonds with three atoms maybe of carbon, we will just say, for example, CH3. So when the subscript is 1, we normally do not write that one. We number when it increases from 1, 2, 3, 4 and so on. Then we write the subscript that is required in order to tell you how many atoms are combined in a fixed ratio. But if one type of an atom, for just like in this example, the subscript there it's 1, but we normally don't write it. Only when it's 2, 3 and 4 we shall do so. So a subscript is used only when more than one atom of a given type is present. Molecular formulas are also used as abbreviations. All right, let us continue. The structural formula for a compound gives the same information as its molecular formula. When you look at the structure through which a molecule is represented, this in essence signifies or has the same information as its molecular formula. This is exactly what you are looking at. In actual fact, you are looking at a chemical reaction that has happened represented in a structural formula, which is the same as a molecular formula. This is exactly what we are looking at. The types and numbers of atoms in a molecule are also made present there. So when you look at the structural formula, you are looking at the types and the numbers of atoms in a molecule. So you are in essence looking at a molecular formula. All right. They say, but also shows how the atoms are connected in a molecule. This is very true. When you look at the molecular representation, the structural representation of methane CH4, we are using the ball and stick model in here. So let's just say it's a structural formula because this is a structure, but we just call this the stick and ball method, the ball stick method of representation. Therefore, we are saying this is a stick, this is a ball, and so on. So at the center here, you have your carbon, only one, and as you can see that the colors are not the same as to represent the different types of atoms that are involved. So you have one carbon atom there, it is in the center, and you have those 4 hydrogen atoms bonded to this one carbon atom in fixed ratios, and the ratio, as you can see, it's 1:4. One atom of carbon bonded to 4 hydrogen atoms. And what is this? This is the structural formula. And the structural formula shows you the types and the number of atoms in the molecule. Because we said now the structural formula for a compound, so this is a compound, gives the same information as its molecular formula. So this is a structural formula that we are looking at, but also gives you the detailed information of its molecular formula. This is very important because this is the molecular formula CH4. We know it's a molecular formula, and we are representing a molecular formula in a structural formula, and it shows exactly the same thing. Exactly the same thing. You have one carbon at the center, and then you have these 4 hydrogen atoms bonded together in a fixed ratio. The ball and stick model, we call that. Another way of looking at this is this way, where we can say, okay, we have a molecular formula, there it is, and then we have our carbon at the center, and you have those 4 hydrogen atoms bonded in that way. We are not going to talk about the valence shell electron pair repulsion theory here and the bond angle between these atoms, and the minimum amount of energy required for the atoms to bond, and the vapor pressure and everything. We are just going to discuss, as you can see here, you just have one carbon. Remember, it has a valency of 4. It can donate or accept 4 atoms, electrons, depending on which type of an atom it reacts with. So it has a valency of 4, and it will form a covalent bond with hydrogen in the first one, the second one, the third one, and the fourth one. So it has a maximum of forming 4 bonds. And because hydrogen has a valency of 1, then you will require 4 hydrogen atoms in order to bond covalently with this carbon. Now here comes a question. Will it be possible if I decide as a chemist that since you carbon, you have a valency of 4, I'm not going to allow you to bond with 4 hydrogen atoms, but only with 3 or maybe with 2? Will it be possible? are we the one dictating whether this carbon should bond with a maximum of 4 or a minimum of 2? Or by nature, this carbon atom, since it was never fabricated in the laboratory and the conditions are there as nature has predicted, and we have found out this via chemical reactions and study of interest, if we can dictate that carbon can bond with only 2, and the reaction is fine that you bonded with 2 but you still has a valency of 2, therefore we can take you with something else that we choose, no matter you accept or not, that you will be able to bond with. Will that be a possibility? Just imagine the catastrophe that we could have on this planet if we were the ones dictating whether these atoms should bond with other atoms based on us dictating even to their very nature how things should be arranged. If it was possible that we can rearrange things naturally as we found them in here, then many things would have been possible. I believe they should have never spent so many years trying to understand chemistry. One should have done exactly as he pleases. But these atoms, these molecules, follows a very distinct nature. You cannot replicate the nature of these things. But I know we can argue and talk about the bombs and many things in here. What I'm trying to say is we have to follow the laws of nature whenever these things bond, and they will always bond with those which they choose to bond with. And we can never tell, even I don't know after how many years, whether these atoms should bond with what and not to bond with. I believe that these atoms bonds, as in this example, carbon bonds with hydrogen because communication was effective between the two atoms, and therefore they will bond. Whenever you try to bring them together and there are so many dissimilar things between two atoms, therefore they communicate and say no matter what temperature you can bring us to, we will never bond. I believe the bonding between these two things is its nature predicted, and we do these reactions just to find out and see which ones they accommodate in order to bond with. We are not the ones dictating who they should bond with. If carbon can bond with hydrogen, that is because they chose to bond as one another. There are many similarities between the two that makes it possible for them to bond, and science or chemistry has never and ever till the end of time will ever be able to understand why carbon can bond with hydrogen and refuse to bond with other atoms. I know that we have studied through time that there are conditions in which they needs to be met in order for these reactions to take place. I understand all that. I've studied chemistry for a very long time. My point that I'm trying to make in here is that for every bond that you have ever seen or that is able to be carried out successfully in the laboratory, that is simply because the communication between the two atoms were effective. And until we have understood enough or having the right conditions for those reactions to take place, they will take place. And some of these atoms cannot bond with each other. Maybe it's simply because there are some missing pieces that we have not yet been able to unravel. And until those times, the types of atoms that cannot bond with each other, it's because we have not yet made the necessary changes that can allow them to bond. This is all what I am saying. But I believe that everything in the periodic table has the capacity to bond with one another, irrespective of whether they are halogens, irrespective of whether they are what, they can bond with one another. What I'm trying to say to you is this. Let me just go to the periodic table very fast. Let me just show you what I am trying to say in here. Okay, let's just go in here and I think I have a periodic table in here, and okay, and in the periodic table I want to show you some few things, very very important things that are worthy of noting. Okay, let me note. Where is it now? I think it has to be somewhere. Okay, let me just look at this one. Right, let's come in here and let me just do this. Right, what is it that we have learned about this last group of the atoms? These ones that are colored in this fashion. What is it that we have learned? We know that they are noble gases and they are closely packed. They cannot accept any atom. These ones, they have completed the octet rule. These ones, right? What I'm saying is they have completed the octet rule because we are limited in terms of knowledge and understanding as to what is happening here. Therefore, we therefore say because they cannot accept any atom, they have completed the octet rule, which is a complete valency of 8. Now, if they have completed the octet rule, these ones, have they completed the octet rule, or there are some levels of chemistry bonding that we have not yet understood that can be able to unlock what we have now set as the octet rule on their behalf? I believe there are quite a number of possibilities. Just because they cannot accept any electrons because they already have a maximum number of electrons, and we have said that they have completed the octet rule. My belief is, even though they have completed the octet rule, we are limited in terms of knowledge and understanding to unravel the mystery behind the octet rule, which we have said they have completed. What I'm saying is this can be able to bond with anything in the periodic table here, just about anything. It can bond with anything. If we have the entire periodic tables in our body, because that's exactly what we are big beings made up of very small material. That is what we are. We come from the dust, and the dust has exactly everything that we have in here. Some of them are not even mentioned in here, which we have not even known them for now. We will even complete the 6,000 years of creation not having understood many of the things here. This periodic table is not complete. There are still many pieces that are missing here. What I'm saying is, even though that they are noble gases, there are so many things that can happen in here. These things, once we can unlock that which is hidden in these noble gases, we can perform, they can react with almost anything that you see in here. But we have not yet reached that level of capacity and understanding, and therefore science says that they have completed the octet rule. But my belief is there are so many things that we still need to understand when it comes to these things. Okay, sorry, that was a lengthy, very lengthy explanation. I'm very sorry for that, but sometimes we need to have questioning minds. We honestly need to have questioning minds. All right, we have read that the structural formula for a compound. Okay, let me just do this. We have read that the structural formula for a compound gives the same information as its molecular formula. The type and the number of atoms in the molecules are also identified there. but also shows how the atoms are connected to a molecule. Hence I said we will not yet talk about the valence shell electron pair repulsion theory, as to talk about many things, the bond energy, the bond length, the angle, the orientation. There's so many things that has to happen before you can have this molecule, but we will deal with that bit by bit. The structural formula for methane contains a symbol for 1C, as we saw, atoms to 4 hydrogen atoms, indicating the number of atoms in a molecule. This is very true. So we have the ball and stick model that shows exactly that as a molecule. So when you are looking at a structural formula, you are in essence looking at a molecule, they said. The lines represent bonds that hold the atoms together. We saw those lines here. There's a covalent bond, so they are covalently bonded with one another. And remember, the one which is more electronegative tends to draw the electron closer to itself. There's so many things that we need to learn about chemistry. The lines represent bonds that hold atoms together. Okay, a chemical bond is an attraction between atoms or ions that holds them together in a molecule or in a crystal. So this is a point worthy of noting, that a chemical reaction is an attraction, because before they can react with each other, they have to attract one another, and the atom with more valency tends to draw an atom with a less valency closer to itself. But these reactions do not just happen randomly for every atom there is. You don't just get to select any atom and then just allow them to bond. No, they have to communicate and get to an arrangement, and that is outside the level and the cognitive understanding of humanity. This is how these things bonds. You just creating circumstances that allows them to bond, but as to what happens behind the scenes shall remain a mystery till the end of time. Right, we will discuss chemical bonds and see how to predict the arrangement of atoms in a molecule later. For now, simply know that the lines are an indication of how the atoms are connected in a molecule. Now, I want us to read back here. We will discuss chemical bonds and see how to predict the arrangement of atoms in a molecule later. So it is possible in chemistry, we read, that we can predict the arrangement of these atoms in a molecule. Very much possible. So we are slowly getting to understand in some of these atoms, if not entirely the periodic table that we currently have. I believe that it is possible that the predictions of the arrangement of atoms in molecules are quite possible, because we are just limited in this understanding of these atoms, and via this little knowledge that we have, there are some predictions which can become true that we can make based on this current knowledge and understanding that we have, and that of our forefathers which have left on our behalf. So for now, simply know that the lines are an indication of how these atoms are connected in a molecule. A ball and stick model shows the geometric. So there's angular arrangement in these atoms. It shows the geometric arrangement of the atoms with the atomic sizes not to scale. Not to scale. Very important. And a space filling model shows the relative sizes of the atoms. So let's just read that once more. A ball and stick model, this is the ball and stick model, shows the geometric arrangement of the atoms. So there are some angles during bonding here that has to be, as you can see even for yourselves here, there's a difference in the angles of bond between or around these atoms. So geometric arrangements of the atoms with the atomic sizes not to scale. So the sizes of these atoms are not necessarily drawn or shaped to scale, and a space filling model shows the relative sizes of the atoms. Okay, that is fine. So that was just the first slide, just giving us an introduction as to the structural formula and the molecular formula of these atoms. Okay, we have figure 2.16. I believe one of them is correct there. I just copied and pasted. A methane molecule can be represented. Remember the methane one, it's this one. Right, a methane molecule can be represented as a molecular formula, as we have saw. A structural formula, we also saw that, and or a ball and stick model. We saw all this, we dealt with all this. And D, a space filling model. Carbon and hydrogen atoms are represented by black and white spheres respectively. We saw that. Although many elements consist of discrete individual atoms, some exist as a molecule made up of two or more atoms of the element chemically bonded together. Very important. Some, not all. Although many elements consist of discrete individual atoms, some exist as a molecule. We call them the diatomic molecules, but we will deal with them. Some exist as molecules made up of two or more atoms of the elements chemically bonded together. So they exist, some of them, by nature. By nature, they have been called to existence in that form. By nature. And they are chemically bonded with one another. We are dealing with the molecules and elements of nature here. So you don't get to decide what happens here, but you only get to decide in making the arrangement that makes what you want possible, if it is possible. Let me qualify that. For example, most samples of elements like hydrogen, oxygen, nitrogen are composed of molecules that contains two atoms each, called a diatomic. Di means two. It's a diatomic molecule, and thus have the molecular formulas H2O2 and 2 respectively, and this is by nature. Very important. Other elements commonly found as diatomic molecules are fluorine, chlorine, and bromine, and iodine. Right, I think I can just go and look into that. Fluorine, chlorine, bromine, and iodine. And they are halogens. We know that they are halogens. For example, we can look at fluorine, which has a molar mass of 18.9984 grams per mole. Very important. And the Latin name is fluoram. English name is fluorine. It was discovered in the year 1810, and so on. It was discovered by Ferdinand Frederick Henry Moisen, was a scientist or a chemist. I do not know. It has 9 electrons, 9 protons, and 10 neutrons. Very important. It has an atomic number of 9, and so on. A density of 0.0017 gram per centimeter cube or cubic centimeter. The melting point -219.67 degrees Celsius, boiling point, and so on. It has a valency of 1 because it is in group 7. It can only accept or donate 1 electron. This is what we mean in order to complete what we call the octet rule. Okay, but let's not go deeper into that. So we have these diatomic molecules that are found in nature, which are halogens. Very, very poisonous. It's a fluorine, chlorine, bromine, and iodine, just to say a few. The most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. Now they say the most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. And as you can see that there's a single bond between these sulfur atoms. There is a single bond. And we can go and look into this sulfur. And we know that sulfur, we have group 8, group 7, and group 6. Sulfur. So sulfur, as we know that it has a molar mass of 32.0648 grams per mole. It's a what now? It's a non-metal, very important. And then it was discovered 2000 BC. Okay, that is fine. It has 16 electrons, 16 protons, and 16 neutrons. We know that. It has an atomic number of 16. Okay, that it's fine. The phase state of the sulfur, it's a solid. We know that. So it is in period 3. It is in period 3. Okay, it is in group 6A. That is fine. And then we can look at many things. The electron configuration, the ion charge of sulfur is S2 minus. So it is S2 minus. It is a minus because it can accept these electrons. Now unfortunately I don't have time to go back to the periodic table. So it has a valency of 2. It can accept 2 electrons. Very, very important that we also note that. So we have sulfur here, it is, and we can see that we have a single bond between these atoms. So sulfur, remember, it has a valency of 2. It will bond with 1 here and bond with 1 there. Please be very careful. You cannot have a double bond here, please, because you have another sulfur atom here. So it will bond with this one with 1 electron, and with this one another 1 electron. So you will have this sulfur atom S8. And we also have the ball and stick model here. And as you can see that there is a geometrical structure. When you look into this, you can see that there's an angle there that makes things possible even here. So there's a geometry that is displayed in this ball and stick model, which you cannot see simply in there. When we are using a structural formula here, it doesn't clearly show us the angles that makes up the molecule, but the ball and stick model gives us an insight view that the angle of which they bond at, it's never and ever the same. It differs with one atom to another, and even as the shapes are not the same and the alignment are not the same there. So these are some of the things worthy of noting. But when we continue further in chemistry, we will deal with these angles and why they have to be the way in which they are. So we are just therefore saying the most common form of the element sulfur is composed of molecules that consist of 8 atoms of sulfur. Its molecular formula is S8. So sulfur, as you can see here, bonds with another sulfur. There's no problem. This is a family of 1. Families accommodate one another. Right, a molecule of sulfur is composed of 8 sulfur atoms and is therefore written as S8. It can be represented as a structural formula, ball and stick model, space filing model. Sulfur atoms are represented by yellow spheres. Okay, it is important to note that the subscript following a symbol and the number in front of the symbol do not represent the same thing. This is true. We know that H2 like this is never the same as that. So this has a different meaning to that. So they represent distinctly different species. H2 is a molecular formula. It represents a diatomic molecule of hydrogen consisting of two atoms of the elements that are chemically bonded together. The expression H2, on the other hand, indicates two separate hydrogen atoms that are not combined as a unit. Very, very important. The expression 2H2 represents two molecules of a diatomic hydrogen. So two molecules of a diatomic molecule, and 2H just tells you that you have two hydrogen atoms, not necessarily bonded together as one. Here you are just telling us that you are having two hydrogen atoms. The expression 2 hydrogen, on the other hand, indicates two separate hydrogen atoms. You just have two separate hydrogen atoms that are not combined as a unit. This is worthy of noting the differences between the two. This one, you have two diatomic molecules of hydrogen bonded together in fixed ratios. And how many of them do you have? Two. So hence they say the expression 2H2 represents two molecules of a diatomic hydrogen. Okay, be that as it may, we are trying to show this difference here. You have one hydrogen atom, a ball, and then this is what H2 means. You're just having two distinctly separate hydrogen atoms, not necessarily bonded with one another in fixed ratios. So we need to note that worthy. But this one is a diatomic molecule bonded together in fixed ratios. A chemical reaction is transpired. And here you have a diatomic molecule, but how many of them? You have two of them. This is what it means. The symbols H, H2, H2, and 2H2 represent very different entities. Compounds are formed when two or more elements chemically combine, resulting in a formation of a bond. For example, hydrogen and oxygen can react to form water, and sodium and chlorine reacts to form table salt. We sometimes describe the composition of these compounds with an empirical formula. We will look at that, which indicates the types of atoms present and the simplest whole number ratio. That's what an empirical formula does, of the number of atoms or ions in the compound. For example, titanium dioxide used as a pigment in white paint and in the thick white blocking type of sunscreen has an empirical formula of TiO2. This identifies the elements titanium and oxygen as the constituents of titanium dioxide and indicates the presence of twice as many atoms of the element of oxygen as atoms of the element titanium. So they say it indicates the presence of twice as many atoms of the element oxygen, twice as many as the elements of oxygen as atoms of the element of titanium. This is what exactly it means. The ratio here will be 1:2. For one titanium, we need two oxygen atom. But remember this is a molecule, just one molecule, but they come as a unit, just as in here, because this occurs naturally in nature as a diatomic molecule. Very, very important that we note that. So we would therefore say here you need one diatomic molecule of oxygen with only one titanium atom. This is exactly what we can say, because we learned in here that by nature this comes as a diatomic molecule, and we are therefore saying you need one molecule of oxygen for every one atom of titanium. Okay, that is fine. And they also said this is an empirical formula. They said, for example, titanium dioxide used as that has an empirical formula of this. An empirical formula. So I will assume let me not make any assumptions. Let me just skip that. Now, when they said titanium dioxide used for protecting your screen, where did we read that? They said, all right, for example, titanium dioxide used as a pigment in white paint and in thick white blocking type of sunscreen has an empirical formula of that. So this is exactly what we are talking about. So when you apply titanium dioxide, because you have two, di means two, so you have titanium dioxide being applied on the foot of an individual here. You can also use a picture of a black man just to show that. Unfortunately, I didn't have time for looking for that picture. So this is the picture that we have. Somebody is applying this titanium dioxide on his foot so that it can protect you from the rays of the sunlight. So what you are simply doing here, when the photons of light strikes you, it will strike this titanium dioxide, and therefore it will provide protection to your very own skin. This is exactly what it will do. And here we have the ball and stick model of this titanium dioxide. Very, very important. This titanium dioxide. I tried to enlarge the picture a little bit here, and we have it in more mass in there. We have 1 2 3 4 5 6 titanium, and we have these oxygen molecules. Remember, by nature they are diatomic. So you will have, remember, 1 2 3 4 5 6. You need to have 6 for that. But remember, oxygen comes as a diatomic molecule, hence you have this reflection of oxygen here, just as a reminder that it's a diatomic molecule. So let's go and look at this titanium. Let me just go and look for this titanium. Here it is, and it is a transition metal. Very important. It has a molar mass of 47.8667 grams per mole, and then its Latin name, it's titanium. English the same. It was discovered in the year 1791, discovered by William Gregor, and it has 22 electrons, 22 protons, and 26 neutrons. And the atomic number, it's 22. Okay, density 4.506 grams per cubic centimeters. Melting point, boiling point. The phase, it's a solid. It comes as a solid. It is in period 4. Very, very important. It is in period 4. And then we have an ion charge. It can be a 3 plus, it can be a 4 plus. Just depends on the usage there. Atomic radius, it's 176. Covalent radius, 148 picometers. Van der Waals radius, 211 picometer. Electronegativity is 1.54. We will calculate all that. Electron affinity, we will look into that as well. The magnetic types, we are not going to go into the details of that. So we just have to know and understand this. And what do you notice here? There's a double bond between the titanium atoms. Very, very important that we note that. So we have carbon, sorry, there it is. And here we have a double bond, a double bond, a double bond, single bond, single bond. Very important. So we have carbon and hydrogen here. We are not talking about titanium. Please be aware. This is carbon to hydrogen bond. This one. So this is something very different. I think this is benzene, but we will deal with that. Let me just leave it. So here we are. So this will be the ball and stick model of benzene. This is benzene. Let's just leave that. This is titanium dioxide. And how many do we have here? We just have 6. So you will have 6 diatomic molecules of oxygen. All right. The white compound titanium dioxide provides effective protection from the sun. A crystal of titanium dioxide contains titanium and oxygen in the ratio 1:2. For one titanium, you need a diatomic molecule of oxygen. The titanium atoms are gray and the oxygen atoms are red. So we have gray as titanium and red as the oxygen atoms. And there it is there, the ball and stick model. Okay, that is fine. As discussed previously, we can describe a compound with a molecular formula and so on. I'm not interested in many of the things that are in here. We talked about the empirical formulas and so on. And this one is for benzene. But let's not deal so much into that. So they just say, for example, it can be determined experimentally that benzene contains 2 elements, carbon and hydrogen, and that for every carbon atom in benzene there's 1 hydrogen atom. You can see that here, and there's a total a bond of 4. It has a maximum of 4 bonds, 1, 2, 3 and 4, because carbon has a valency of 4, so it can form 4 bonds. And thus the empirical formula is CH. Remember, for they said now carbon they said experimentally that benzene contains 2 elements, carbon and hydrogen, and that for every carbon atom in benzene there's 1 hydrogen atom. So the ratio is 1:1. Therefore the empirical formula will be CH. So for 1 carbon atom you need 1 hydrogen atom. An experimental determination of the molecular mass reveals that a molecule of benzene contains 6 carbon atoms and 6 hydrogen atoms. So the molecular formula for benzene is C6H6, and I can divide here both sides by 6, leaving me with CH. So CH will be the empirical formula and the molecular formula will be C6H6. All right, that is fine. Very much fine. So this is benzene. I'm not going to go into so much detail. If we know a compound's formula, we can easily determine its empirical formula. We saw that. That's fine. For example, we have here C2H4 and O2. I can divide throughout by 2, leaving me with CH2O, which is the empirical formula for what now? For okay, sorry, let me do this. Let me just look at what this molecule is. It's a vinegar. It's vinegar here. We have a vinegar here. All right. The reverse chronology is generally followed in the actual practice. For example, the molecular formula for acetic acid There it is, the molecular formula, and this is the symbology through which it is represented. This is the ball and stick model of the acetic acid, so which is vinegar here. So we have vinegar C2H4O2, and if we were to write the empirical formula, you divide it by a number that goes into all of them without leaving a remainder, which is 2, and you will end up with that. So this is just something very important that I wanted us to note and understand. And when we have done that, guys, I will see you in the next tutorial.